Welcome to the second part of the lecture about ultraviolet visible spectroscopy. And in the first part, we looked at the instrumentation that is used to record the absorption spectra with in UV visible range. And in this part, we are going to now look at the spectra and see why these spectra are being produced, and also look at the quantification specifically. So as I told before, this is an absorption spectrum. This means that we measure how much light is being absorbed by the molecules when these molecules are being exposed to the light of a specific wavelength. And what happens with the molecules in the ultraviolet visible spectroscopy is that the ground state molecules are absorbing the quantity and therefore going to an excited electronic niveau, excited state, which we denote then by the molecule and the star. And in order for these molecules to absorb in the ultraviolet visible light region, the difference in the energy of the ground state and the excited state has to match the wavelength uh, the, which we are exposing our molecules to. So when we are having very energetic quantize, so for example, in the vacuum UV region, so below 190 nanometers, then very many molecules are absorbing because this wavelength is energetic enough to cause excitation for many, many molecules. However, when our quanti have less energy, so when they are in the ultraviolet or in the visible range, then we need this excited states to have a bit lower energy relative to the ground state. And one important parameter here is that pi electrons are very important because pi electrons usually have lower energy in the excited state. So the more pi electrons are present, the more likely it is that we obtain absorption of the molecules in the ultraviolet visible range. And the more conjugated bonds, so more the pi electrons are conjugated, the longer wavelength we usually can expect our molecules to absorb. Um, so it is very important that the molecules contain double bonds, and also the more double bonds there are, the longer wavelength we can use to measure these compounds. In case of transition metals in the solutions, we usually see some kind of a transition metal water molecules or other additive complexes. And for these transition metal solvent complexes, we also very, very often see absorption in the ultraviolet visible range. And this is also already clear from the color of the solution. For example, if you think about the copper solution, then this has a very nice blue color, which comes from the copper and water molecules complex that is formed when dissolving a copper 2 salts. So this is important. Also, complexes which undergo charge transition from the metal to the ligand or vice versa are having very intensive long wavelength absorption peaks usually. Now let's look at a few examples. First thing is it is an example spectrum. All of them come from the NIST web library, and you can visit NIST web page to look multiple compound spectra to see how they generally look. And here we have pentadiene, and this has two double bonds, and this compound does absorb light in the ultraviolet region, but it's very tiny amount that is absorbed in the ultraviolet region. In its absorption maxima is actually in the vacuum ultraviolet region, so below 190 nanometers. So compounds which don't contain any double bonds, such as alkanes, are absorbing even at lower wavelengths. However, now when we look at an isomer of this compound, where the two double bonds are conjugated in this molecule, so we can have a resonance structure where the double bond moves to the middle, then we see a significant shift in the absorption maximum of this compound. Before it was about 190 or below, and now we have it in the ultraviolet region, so at 220 nanometers. And this compound actually can be measured in ultraviolet spectroscopy because its absorption maxima is now in the ultraviolet region. And this clearly shows that in the first example, we have two isolated double bonds, so the wavelength is shorter, while now when we have two conjugated double bonds, the wavelength is shifting to a longer wavelength. However, if you look at an even larger system, so a benzene molecule, which also has an amino groups and a nitro group, which also both can have resonance structures. So nitro group itself has already a double bond which can be conjugated, as well as amino group can contribute with electrons to this pi system in the benzene ring. And then what we see is that we can have very many absorption maxima here. So the longest wavelength here at which we have an absorption maxima is already in the visible spectrum, so at about 400 nanometers. So here we made the conjugated system even larger. We added electron donors to the system, and the wavelength of absorption maxima shifted to larger wavelength. What we can also see from here is that all of the absorption spectra have very wide absorption maxima. So usually the maxima is multiple tens of nanometers wide. So the absorption maxima are really wide in case of molecular absorption. And this comes from the fact that when our molecules are excited to the excited state, then they can be excited to multiple different vibrational or rotational excitation niveaus, so which means that there are really many possible combinations of the wavelengths, radiation wavelengths that can be absorbed by the molecule. So this fact that the molecules are absorbing at a very wide wavelength regions means that selectivity can be a very big problem in ultraviolet visible spectroscopy. So usually identification of the compounds based on the spectra is not really possible because the peaks are just so broad and it's not really selective to any compounds, which, for example, is different than in IR, where we will later see that the peaks are narrower and these peaks can be associated with the specific functional groups. However, ultraviolet spectroscopy is very useful in quantitative analysis. And the quantitative relationship between the absorbed light at the wavelength lambda is associated with the concentration of the solution in a linear manner. And this association is called the Lambert-Beer law, and it tells us that the absorption at the wavelength lambda is proportional to the concentration of the analyte. It's also proportional to the optical path length, or the optical length, so essentially the width of the cuvette. And it's also proportional to something which is called the molar absorption coefficient of the analyte at the specific wavelength. So this means that when we double the concentration, the absorption of the compound is increasing 2 times. When we make the path length longer, then also more is absorbed. And this is very logical because when we make the cuvette twice longer, then twice more compound molecules can be on this optical path when the light is passing through the sample holder, the cuvette, which means that it's also twice more probable that the light is being absorbed. So optical path length, for example, is something that can be optimized to obtain better sensitivity for low concentrations. So there are different cuvettes with different length that can be used. And also there is a very important part here is the molar absorption coefficient. And this molar absorption coefficient is specific to a compound and specific to the wavelength. And it describes how much is a compound absorbing at a unit concentration at this specific wavelength. So the larger these values, the more is the compound absorbing light. And of course, absorption is calculated from the absorption measurements from the intensity of the light without analyte, so before the sample, or actually this is measured from the Planck cuvette, and the intensity of the light after passing through the sample. So now to actually use the Lambert-Beer equation for quantification, there are a few limitations. Lambert-Beer law is a low concentrations law, which means that it does not really apply for very high concentrations. And usually we can set limits that if the absorption is about 0.1, 0.02 absorbance units, usually denoted by AU in the literature. So this is either referring to absorption units or arbitrary units, even though absorption actually doesn't have units. So the absorbance needs to be higher than this usually and less than about 1.2 to actually for the linear relationship actually to hold. However, there can be different other limitations. And usually this corresponds to the concentration range of about millimolar to 0.01 millimolar. But this depends on the compound and how large are the molar absorption coefficients for these compounds. And also, it also depends on the wavelength that we use. Usually the linear range is not very wide, so measuring samples which have very wide concentration range might require concentrating or diluting the samples so that the samples actually fit in this relatively narrow concentration range. What is positive here is that the calibration graphs are usually very stable. This means that if the calibration graph is measured in the morning, they usually fairly well holds during the day or even on the next day, so that the calibration graph does not need measuring very, very often, which, for example, is often observed in, for example, in mass spectrometry that you will see later in this analytical chemistry course. But in ultraviolet visible spectroscopy, the calibration graph usually holds very well. And the reason for this is that there aren't very many parts of the instrumentation that can change during the time. So there aren't very many moving parts. So the monochromator, yes, there are moving parts. There is a motor that is turning it, but this is very well reproducible and also necessary for us to be able to rely on the accuracy of the wavelength. What is also important here is that there aren't too many adjustable parameters. So usually when what we are adjusting is the cuvette length, and also the wavelength on which we are doing measurements, but there aren't very many more other parameters that would need adjusting and then remeasuring the calibration graph. So from this point of view, it is a nice, robust technique. However, if possible, then of course measuring the calibration graph as close as possible in time to the samples is still suggested. What is also important is that this all is valid only when the instrument has warmed up. So this means that immediately when we plug the instrument in and put the lamp on, the lamp will start heating. And during this time, when the stable temperature of the lamp is not achieved, then the radiation intensity of the lamp and the radiation profile of the lamp will change. And this is not super good for quantitative measurements as well. And it's also true for the detector. So detector also uh, can somewhat change with the time, essentially, especially when the when the temperature is changing. So now, why there are these limitations in the Lambert-Beer law? And there are actually three types of limitations. There are real limitations, there are chemical limitations, and there are instrumental limitations. So when we talk about real limitations, then this comes from the fact that Beer's law is meant to apply only for diluted solutions. This means that it applies for molecules which are not influencing each other. So the molecules are so far from each other, swimming in the solution, that they are not influencing each other as electronic clouds, and therefore the way they absorb it. However, if the solutions become more concentrated, then the distance between the molecules in the solution is decreasing, and these molecules start interacting with each other and deforming each other as electronic clouds, and therefore also the energy niveaus at which they are absorbing light. So when we make the solutions more concentrated, the Beer's law, which assumes that the electron clouds of the molecules are isolated and are not interacting with each other, is not simply applying anymore. Another limitation is the chemical limitations. And with chemical limitations, we mean all kinds of chemical processes that can happen to the molecules in the solution and therefore alter their absorption spectra. So for example, associations, dissociations, reactions that could occur. The simplest example is that if we are measuring compounds which are pH sensitive, for example, indicators, and we don't buffer the solution, then with the increasing concentration, the pH of the solution will change, and therefore also the ratio of the neutral and ionic form of this indicator will change. And of course, we'll see also then the shift in the absorption spectra with this pH change. So therefore, if we are measuring compounds which could dissociate or associate, then this needs to be taken into account, or actually, if possible, ruled out by, for example, buffering the solution before doing the measurements, so that the pH would not change from sample to sample, or from standard to standard, or from sample to standard. There are also instrumental limitations. For example, Lambert-Beer law actually applies for a monochromatic light. So this is for light with one very narrow wavelength. Also, stray light can cause deviations from the linearity, as well as if the measurement cuvettes are not matched. And these are limitations for the higher concentration level is usually, but the lower concentration level limitation comes simply from the reproducibility. So when we are dealing with absorption with very low absorptivity, so for example 0.01 absorption units or arbitrary units, then actually only about 2% of the light is being absorbed by the sample, which of course means that actually the I0 and I are very, very close to each other, and the reproducibility of the measuring of the intensity of the light is now determining how low can we go with the absorbance that we can measure. And this is then now the instrumental limitation that we can differentiate between such small differences in the intensity of the I and I0. Now, when we look more deeply into the polychromatic radiation and the limitations that this is causing, then as said, Baer's law is applying for monochromatic light, so for light at a very narrow one wavelength. And this also determines how we should select the wavelength that we are using in our measurements. So the question could be, would it be better to measure here at the maximum of the spectrum, or would it be better to measure here at the slope of the absorption peak? And this actually is directly related to the fact that Baer's law applies to the monochromatic light. So if we are now taking an example case where we measure the light on two wavelengths, lambda 1 and lambda 2, then the absorbance that we are measuring in total is actually the sum of the I0s and taken the ratio to the sum of the I's. So the intensity of the light on these two wavelengths before and after the sample cuvette. And when we transform this by adding in here the Baer's law, where we substitute the I with the I0 and with the molar absorption coefficient, the length of the cuvette and the concentration, then we can see that the ratio, then we can see that the total absorbance is not anymore directly linearly related to the concentration. And this linear relationship applies only if the molar absorption coefficients for our analyte at these two wavelengths, lambda 1 and lambda 2, are equal. So only if the molar absorption coefficient is very, very close for these wavelengths that we are measuring together, only then actually the linear relationship between the absorbance and the concentration is valid. And now when we look here in the band B and band A, then we of course see that this is rather true for the band A. So at the maximum, if we are slicing out a tiny range of wavelengths, then the molar absorption coefficient for these wavelengths are much closer to each other than they are here at the slope of the UV-Vis spectra. And when we now are interested what differences in the epsilon cause how large deviations from the linearity, then in the case we are having these two wavelengths and the epsilons for the two wavelengths, so the molar absorption coefficients are very similar, then we see a nice linearity here. However, if the absorption coefficient for one of the wavelengths is about 3 times higher than for another one, then we see slight curvature. And if this difference becomes even larger, then we see a stronger curvature in the calibration graphs. So measuring at the wavelength range where the absorbances are very, very similar is advantageous to get the good linearity. And of course, this therefore implies that at band A, we get a better linearity than for the band B, because here the absorbance coefficients are differentiating much more this compound. Another limitation is the stray light. And stray light is any kind of light that might accidentally get to the detector, then that is not influenced by the absorption of the light in the sample. And these are, for example, stray lights which come from not completely sealed covers in the instrumentation, or from random reflections of the lamp, of the light coming from the lamp that hit the detector. So all kinds of stray lights. And when we assume that the stray light intensity is I stray, then the absorbance equals the logarithm of the I0 plus the light intensity that is coming from the stray light. So we can't differentiate between the actual I0 that is supposed to hit the detector and the stray light that is hitting the detector. And the same is also observed when we measure the sample. So we actually see the sum of the intensity of the light that is actually passing through the sample and the stray light. So as a result, the linear relationship is not anymore preserved. So when the stray light is relatively small, we see the curvature at the higher concentration. So cases where more light is absorbed, where I is much smaller. But when the stray light is very intensive, so there's very much of the stray light, then the impact already starts at lower concentrations. And this is, for example, one reason why it's very important to close the cover of the UV spectrometers very carefully and very tightly to avoid any kind of light hitting the detector from our environment, to avoid this kind of issues with the stray light. Additional important factor with the closing the covers is that also during the times when you are not actually doing measurements, the cover should be closed to avoid any light that is coming from the environment to hit the detector. And many instruments have an automatic switch that blocks the light that could come from the environment to going to the detector, but some don't. And in these instruments, it's important that the light from the environment does not go to the detector, because that can make our detector a bit blind. So it is hit by too many photons at a time, and it becomes less sensitive. And now, when we do the quantitative analysis, then it is important to know what are the factors that are affecting the molar absorption coefficient in order to choose the measurement conditions wisely. As we saw from the spectra that looked, then we saw that for one compound at different wavelengths, the absorbance was really different. And this comes from the fact that the molar absorbance coefficient is changing with the wavelength. So it depends very, very strongly at the wavelength, and choosing the good measurement wavelength is very important in ultraviolet visible spectroscopy. It also strongly depends on the compound. We saw that that compounds with more conjugated systems absorbed at longer wavelengths, where compounds with less conjugated systems did not absorb at all. So at this wavelength, these two different compounds have very different molar absorption coefficients. It also slightly depends on the environment. So, for example, pH when we talk about solutions, and also on the solvent. But these effects are not so influential for all compounds. So, for example, for the pH is important for compounds that are themselves acids or bases, and which have then a significantly different molar absorption, that have different spectra for the form that is neutral and that is ionized. And this is, for example, a case for most indicators. So indicators in nature have this effect of the pH on the ultraviolet visible spectrum. Also, temperature and strength and the solvent can have an effect, and the extent depends exactly on the compound, but usually it's not super big. It's important to mention that the molar absorption coefficient does not depend on the concentration, and this is why the linear relationship between the absorption and the concentration is expressed in the Lambert-Beer law like it is. Let's look a bit at the impact of the environment. So one aspect that can be influential is solvent or the lack of it. So here is a spectrum of a triazide at a gas phase, hexane solution, and aqueous solution. In the gas phase, we can see a fairly fine structure of the spectra. And this comes from the fact that in gas phase, the molecules are free to rotate. So we start also seeing the individual rotational excitation levels in our absorption spectrum. However, in hexane, the rotation starts to be hindered, but we can still see different vibrational levels. So we see that there are different bands here. But for aqueous solutions, both the vibrational and rotational levels are meshed, are blended into one big peak, and we see actually a very not characteristic spectrum here with a very bright, broad absorption maximum. So if you want to really investigate very thoroughly the fine structure, then gas phase or non-polar solvents are much better for this kind of studies. And also, as mentioned before, pH has an effect. So here is an example of a tumor blue and how its spectrum depends on the pH. So at a very low pH, it has an intensive absorption maxima. It at about 560 nanometers. It is primarily in this form, but when the pH starts increasing, then it goes over to the anionic form, and the absorption maxima is the absorption maxima shifts to about 440 nanometers. And in between, we actually have a blend of these two forms, and our spectrum also is a blend of these two spectra. And for studies of such compounds which have two different forms with two different spectra, usually the molar absorption coefficients are expressed separately for the neutral form and for the anionic form or cationic form, depending on the compound. So when we are now choosing the wavelengths, choosing the conditions, then it is very important to consider at what wavelength we are doing the measurements. So usually the spectral bands are very wide, and this results in a problem that the spectra are not very selective. So if we have a mixture, and most of our samples are mixtures, then it's very likely that the compounds in our mixture are absorbing at least partially at the same wavelengths. So there are at least some wavelengths at which both of the compounds or many of the compounds in the sample are absorbing light. So this means that on its own, ultraviolet visible spectroscopy has fairly low selectivity. This selectivity can sometimes be increased, especially for metals, by adding photometric reagents. So these are ligands in case of metals that form very long wavelength absorbing complexes, so colorful complexes with the metal, and which are then much more selective as well. And in these cases with photometric reagents, there are usually twofold selectivity. Firstly, the reactivity of the metal with the photometric reagents, so that the reagents would be already selective in reacting with only some of the metals, not all of the metals. And additionally, the wavelength, which is shifting usually to longer wavelength, and the um, the overlap with the absorption bands of the other compounds in the sample is thereby decreased. So almost all compounds absorb when we are going with our wavelength to very low wavelengths in the very low end of the ultraviolet region. So at least to some extent. So this means that if possible, we actually don't want to to do our measurements at the very low wavelengths. If we have aromatic compounds, then they almost all absorb at the wavelength lower than 270 nanometers. And if we have compounds for which we already see with our eyes that they are colorful, then it is very possible that we can measure them at the 400 or above nanometers. So what can be done is that quantitative analysis can be performed very nicely with ultraviolet visible spectroscopy if the analytes are absorbing at very long wavelength, because then the probability of other compounds absorbing at the same wavelength is reduced, because most compounds absorb at the lower wavelength, but with increasing wavelength, the probability is decreasing. So if we know that our compound is absorbing at very high wavelength, we can be fairly sure that this could be possibly selective. Of course, knowledge about other compounds potentially present in the sample is very advantageous, because then we can also evaluate the possibility of these compounds interfering with our measurement. Another very useful information piece can be that if we know that other compounds are absorbing at very low wavelength, even if the compounds analytes themselves don't absorb at so high wavelength. So for example, if we try to measure the aromatic compounds in alkane mixture, so then we know that there are almost alkanes and aromatic compounds, and we are interested in the aromatic compounds which absorb at the UV range, so up to 270 nanometers. But we know that the alkanes don't absorb in almost at the UV region. They are mostly absorbing in the vacuum UV, and therefore we can say that, okay, our matrix compounds, so the alkenes, are not interfering with our measurements, even though the analytes itself did not absorb at so high wavelength. Another possibility for increased selectivity is if we can separate the analytes from the other compounds. And this, for example, is the source of great success of chromatography coupled to UV-Vis spectroscopy. So this is really, this has been a large breakthrough in quantitative analysis over the decades. So this separation really provides increased selectivity, and therefore also very reliable quantitative analysis. Additionally, sometimes we can transform our analytes to a form where they absorb at much longer wavelengths. So this is, for example, case for these metals where we use a photometric reagents to create compounds and to create complexes that absorb at very long wavelength. So the higher the wavelength, the more likely it is that only our analyte is absorbing. Now, another consideration is also the molecular absorption coefficient. So the higher the molecular absorption coefficient, the more sensitive are our measurements. So this means that, of course, we would like to measure at the peak maximum. And measuring at the peak maximum is also good to preserve the linearity as we saw before. And now when we go back to a spectrum that we had before here for the orthonitroaniline, then we have here three different wavelengths that have been marked as the maxima. And the question now here is which kind of wavelengths to use for the quantitative analysis. And I give you a second to think about it. Okay, maybe you thought which wavelength you would use for this kind of analysis, for quantitative analysis of the nitroaniline based on the spectrum. And now the question is, what are the important considerations? Firstly, I could see here two possible answers, but one of them is correct. So one possibility to view this is based on the absorbance. So to aim for the highest absorbance. So for example, choose the lambda 1, so at about 230 nanometers, because this has the largest molar absorbance coefficient. However, the problem here is that at lambda 1, the wavelength is very low, and very, very many compounds, including many aromatic compounds, are absorbing light here. So this means that this is utterly not very selective wavelength to do measurements at. So if there are other wavelengths at which there are there are absorption maxima for this compound, then higher wavelength is always suggested, even if the sensitivity might be lower. So we could consider measuring at lambda 2, but the molar absorption coefficient here is not actually any higher than at lambda 3, and also lambda 3 is significantly higher wavelength. It's actually in the visible region. So this means that now only colorful compounds could be interfering with our measurements. So this means that lambda 3 here is much more suited for the quantitative analysis than the lambda 1 or lambda 2, even though its molar absorption coefficient is not the highest of all of these wavelengths. So all in all, it's very important to consider the wavelength when designing the quantitative analysis experiments, and the highest possible wavelength is always suggested, and if possible also taking into consideration the intensity at the wavelength or the molar absorption coefficient is important.